Good evening, friends. My name is Pankaj Dumka. Today, we will be discussing about entropy. And before I start talking of entropy, I would like to tell you, or basically, I would like to remind you that we are talking of macroscopic thermodynamics. So, we will be talking of entropy in terms of macroscopic thermodynamics. Now, now you know that the first law of thermodynamics, when applied to a system performing a process. First law, when applied to a system performing a process, gives you a property which you know as internal energy. That means, first law, when we apply to a process, we will get internal energy, like delta U is heat transfer in that process minus work done by system in that process. Now, likewise, when second law of thermodynamics applied to a process gives us the concept of entropy. Basically, if you look, the thermodynamics is a study of three E's. What are these three E's? The first one is equilibrium, the second one is internal energy, and the last one is entropy, which is the topic of discussion today. Now, before we start talking of this, let us see from where we got the clue of entropy. Consider a reversible adiabatic line or a reversible adiabatic path performed by a system. And consider another reversible adiabatic, and let us say they are intersecting at point A. These two are reversible adiabatic. Now, you bound this curve, you close this by a isothermal curve. And these are reversible adiabatic. So what is happening? A cycle, you can see a cycle. Let us say this is point A, this is point B, this is point C. So this system is performing a cycle. And you know the area of this cycle will give you the work done. That is W. And if you see the total amount of heat interaction in the cycle, as these two are adiabatic, so there will not be any heat interaction. So the sole amount of heat interaction in this cycle is in this isothermal process. So if you apply the first law of thermodynamics to this cycle, you will get this heat transfer in the isothermal process is equal to W. That means you are forming an engine which is interacting with a thermal energy reservoir, only single thermal energy reservoir, and in turn it is developing the work which is equal to the amount of heat transfer to this. That means you are forming an engine whose efficiency is 100%, which is the violation of Kelvin-Planck statement, hence not possible. Hence, what is not possible? The thing which is not possible is two reversible adiabatic lines can never intersect. So these two reversible adiabatic lines can never intersect. And we know that only two constant property lines can never intersect. For example, consider the same plane, PV plane, and consider a constant pressure process, P1, and lower constant pressure process, P2. They will never ever intersect. They will always be parallel to one another. Likewise, two constant volume lines, V1 and V2, they will always be parallel. And if volume becomes same, they will overlap but never intersect. Hence, we can say that a reversible adiabatic line must be having some property. It will be showing some property. Or a reversible adiabatic line is a line of a constant property, or it is a constant property line, and that constant property line is yet to be defined. But as we are talking of entropy, so it is clear that that has to be entropy only. So let us talk of Clausius theorem. Before we start talking of Clausius theorem, let us consider a PV plane and a general curve starting from point A and finishing at point B. This is the process performed by any system. And this is the area under this curve. That means the work done will be area under AB. Work done in AB path, this path. You do one thing, you take one reversible isothermal line, another isothermal line, a reversible adiabatic line, another reversible adiabatic line, and place a reversible isothermal in between these two such that, let us say this, such that the area under this A, let us say this is C and this D, the area under this A, C, D, B, the area under A, C, D, B becomes equal to area under original path, that is AB. Now write first law of thermodynamics for these two processes. Let us write first law for the process AB. So the heat transfer in this process will be change in internal energy, that is UB minus UA plus WAB. So now let us write for ACDB. So heat transfer in ACDB will be change in internal energy plus WACDB. Why I am writing UB minus UA? Same as above. The reason being, as internal energy is a point function, so it will be immaterial whether I am following the path A to B, from A to B this, or whether I am following this path. This will be the same because internal energy doesn't depend on path. And the choice of these two, adiabatic and this isothermal, is such that the area under ACDB is same as area under AB. That means the work transfer in the process A to B is same as the amount of work transfer in the process ACDB. So by this you can conclude that the heat transfer in original process AB is same as heat transfer in the process ACDB. So what you did? You have replaced this path by three paths, or in other words, any reversible path. This AB is a reversible path. This can be replaced by a reversible adiabatic followed by a reversible isothermal followed by a reversible adiabatic, such that the heat transfer in the original reversible path is same as the heat transfer in the isothermal process. So now we are in a position to learn Clausius theorem. Let us consider same PV plane and any reversible path followed by a system which ends at the same point where it started, that is, consider a reversible cycle. Now do one thing, divide this cycle by number of reversible adiabatic paths and close all these paths with reversible isothermal. So what you did? You have a cycle, you partitioned it by so many reversible adiabatic and closed these reversible adiabatic by reversible isothermal paths. So if you consider one such let us say this one A, or let us consider this one. If you consider this, so this is what you have formed a Carnot cycle. How? This is a reversible isothermal followed by a reversible adiabatic, then followed by a reversible isothermal, and again reversible adiabatic. So you are forming one Carnot cycle, not only one. The whole figure has been divided into a number of Carnot cycles. And the heat transfer in this original cycle will be the same as heat transfer in this isothermal, just we have seen. So let us say the heat transfer in this small cycle will be dq1 and this is dq2. And this heat transfer is taking place at temperature T1 and this is at temperature T2. Likewise, for this another cycle, this cycle, consider the heat transfer is dq3 at temperature T3 and here it is dq4 at temperature T4, and likewise. So for one such cycle you can write dq1 by T1 is equal to dq2 by T2, Carnot's theorem, or dq1 by T1 plus minus dq2 by T2 is equal to 0. For second one, it is dq3 by T3 plus minus dq4 by T4 is equal to 0, and likewise for everyone. So if you add or sum up these, dq1 by T1 plus minus dq2 by T2 plus dq3 by T3 plus minus dq4 by T4 up to so on, this will give you 0. And here these minus signs simply means that this is the amount of heat which is rejected, nothing else. If you are in connection with this, so it is okay, no problem. So this whole, so if the number of these cycles is very large, huge, then you can say that the cyclic integral for this dq by t is equal to 0, and this r. Why this r? Because this original path is a reversible. So this heat transfer in a reversible path or cycle to that of temperature at which this heat is getting transferred in a cycle will be 0. This is called as Clausius theorem. Now you know this. Now it is a time to define property of that reversible adiabatic path. And before that, let us see something. Consider the same PV plane. Starting point is A, then B. This is the path performed by any system, and that too reversible one. And that system is brought back from B to A by another reversible path R2. So if we apply Clausius theorem onto this, we will say that dq by t for this path R1, R2 will be 0. And if we want to split this, or I mean to say, if we split this, that is adding up this dq by t for this path plus for this path will be 0, means dq by t from A to B along path R1 plus from B to A again dq by t along path R2 will be 0. Or if you want to write, you can write the same thing as A to B dq by t along path R1 plus B to A dq by t along path R2. This is 0. Bring this term onto right side. A to B dq by t along path R1 is minus B to A dq by t along path R2. As this process B to A is a reversible, so it will be immaterial if I go from here to here. That means as this is a reversible process, so I can revert this process back. And in turn, what will happen? The effects which this system has created while going from A to B will get reversed while coming back from A to B in revert direction. That is, if the system is liberating heat to the surrounding from while going from B to A, then it will gain heat, the same amount of heat from surrounding while coming from A to B. So this will be from A to B from path R2 dq by T. So what is happening? That the ratio dq by T from A to B in path R1 is same as this integral in path R2 while going from A to B. That simply means that this dq by T is independent of path. And what are the things which are independent of path? Those are point function, or those are properties of system. Hence, this dq by T is a property of a reversible path. So, this dq by T is a property, and this property is known as entropy. So if you integrate this from any point, say 1 to 2, so this will give you the change in entropy along the path between the points 1 and 2, this, provided you are talking of a reversible path. Because you can perform integration only on a reversible path. Now, consider a case that your system is moving from 1 to 2 along this irreversible path. This dotted line means irreversible path. And now it is asked to find out what is the change in entropy from this point 1 to this point 2 while the system has moved from 1 to 2 along this irreversible path. And you know this, but you will stuck. Why? Because this integration can only be performed on a reversible path, and you have a irreversible one. So what? It will be immaterial. Why? As entropy is a point function, so we will replace this irreversible path by a known reversible path. And the moment we know this, we can find out integration dq along this reversible path by T from 1 to 2, that is delta S, will be same as irreversible entropy change along this irreversible path. It's as simple as possible. Now, talking of temperature entropy plots, and talking of the same clue now you know that this ds is dq by T for a reversible process. Now, what is this S? This is entropy. And what type of property? This is extensive. That is, it depends on the extent of system. That is the mass. So ds by dm will be intensive property. That is intensive or specific entropy. Now, if you talk of a problem where the heat transfer is 0, let us say consider a problem where heat transfer is 0 along this reversible path. So what will happen? This ds will be 0, or S is constant. So along a reversible adiabatic path, entropy is constant, or in other words, a reversible adiabatic path is also called as isentropic path, or the process is called as isentropic process. Now consider this plot, temperature entropy plot. Why I am considering this? This will be clear from here. Look friends, this dq along a reversible path is TdS. So if you have any reversible path 1 to 2 in this TS plot, this is intensive entropy, and you consider a small strip ds at temperature T, so the area of this will be TdS. So if you sum up from 1 to 2, you will get what? You will get the total heat transfer in this process. So any curve in TS plot, area under that curve in TS plot will give you the amount of heat transfer in that process. So if you have consider a Carnot cycle, two adiabatic, two isothermal process. So in TS plot, this is what? This is a isothermal process, that is a constant temperature line. This at higher temperature, this is another. This is T2, this is T1. So friends, these are what? These are reversible adiabatic. Reversible adiabatic means isentropic, means entropy is constant. So these are those isentropic lines. So you are left with what? You are left with a cycle which is rectangular looking cycle, and this rectangular looking cycle in TS plot is nothing but Carnot cycle. So if you are interested in efficiency of this, if we consider this as delta S, so it is 1 minus Q2 by Q1. What is the Q2? Q2 is the amount of heat loss. What is Q1? Q1 is the amount of heat gain. So 1 minus Q2, Q2 will be area under this line, that is T2 into delta S, this T2, this length into delta S. What is T1? It is area under this line, that is this whole T1 multiplied by this delta S. This will get cancelled, so efficiency is 1 minus T2 by T1. You already know this. Now, the last topic of today's discussion will be the inequality of Clausius, or Clausius inequality. Clausius inequality. You just now have seen equality, that means for a reversible one. So it is obvious this will be for irreversible case. So consider in this TS plot a cycle. What type of cycle? A general cycle. Let us say A, B, then C, and then D. So this is your cycle in this TS plot. And what is so special about this cycle? I am considering that every process in this cycle is reversible except AB. That is, let us consider this AB is any general cycle. It can be reversible, it can be irreversible. Right now we don't know. So AB is any general cycle, whereas BC, this is CD and DA, they all are reversible cycles. And what is BC? BC is reversible, this is a specific volume. This BC is a reversible adiabatic line. Similarly, AD is reversible adiabatic line, and this DC is isothermal line. So you do one thing, as you did in previous case, divide this whole cycle into number of divide this whole cycle by number of reversible adiabatic paths, and close the upper path by isothermal lines. So this will give you so many Carnot engines. Look, reversible isothermal, then reversible adiabatic, then reversible isothermal, then reversible adiabatic. A Carnot engine. Likewise, so many. So consider one such cycle. Let us say this one. I am considering this one. This Carnot cycle. So the heat transfer here is dq, let us say, at temperature T, and this temperature be T2. So the heat transfer here will be dq2 at temperature T2. So the efficiency of this cycle, efficiency of this cycle will be what? It will be 1 minus dq2 divided by dq. So what will be the efficiency of a reversible cycle? Let us, as this is not a reversible one, this is a general cycle. It can be reversible, it can be irreversible. So if, let us say, if this is a reversible cycle, then the the efficiency of a reversible cycle between same temperature limits will be 1 minus dq2 by dq. This is reversible. And we know from the Carnot theorem that it says that the efficiency of a reversible cycle will always be more than the efficiency of a irreversible cycle working between same temperature limits. That means 1 minus dq2 by dq will always be less than or equal to 1 minus dq2 by dq for a reversible case. This equality is for when this is reversible, and this inequality is when this is irreversible. So you can write that minus dq2 by dq will be less than equal to minus dq2 by dq for a reversible case, or dq by dq2 will be, if we let us do this one, dq by dq2 will be more than equal to dq2 by dq for a reversible case. Negative signs, when negative signs multiplied, this inequality will get reverted. So this dq reversible by dq2 reversible will be less than or equal to this dq upon dq2 for general cycle. Now we know that for a reversible cycle, dq reversible by dq2 reversible, that is for reversible cycle, it is nothing but t by t2. So t by t2 will be less than equal to dq by dq2, or this dq by t, this dq by t will be I did some mistake, I think, friends. This dq2 by dq for this is this, it is correct. dq2 by dq will be more than equal to this. So this is the problem. This dq when come here, this will be more than this. So if this is the case, then this t by t2 is more than this, or dq by t will be less than or equal to dq2 by t. What is dq2 by t? It is the heat transfer in case of a reversible process, and heat transfer in case of reversible process to that of temperature at which this heat is getting transferred. So what is this? This is nothing but the change in entropy for this in small process. So these all are path functions, these are not point functions. So dq by t will always be less than or equal to ds. This is inequality of Clausius. Or if we consider for the whole cycle, that is cyclic integral of dq by t will always be less than or equal to cyclic integral of ds, and as s is a point function, So cyclic integral of dq by t will always be less than equal to 0. That means if the process is irreversible, then the cyclic integral of dq by t will be less than 0. If it is reversible, then the cyclic integral of dq by t will be 0. And if at all any case you come across where this dq by t is coming out to be more than 0, then it is certain that this is not a possible case. That means if in any process the cyclic integral of dq by t is coming out to more than 0, that means it is the violation of Kelvin-Planck statement. It is the violation of Kelvin-Planck statement. Let us see how this is not possible. So consider any general cycle. Let us consider this general cycle onto this plot. Any general cycle. In this cycle, some amount of heat is getting transferred. Let us say Q1 amount of heat is transferred at T1 and Q2 amount of heat is transferred at T2. Now, for this cycle, from the Clausius theorem, if it is given to you that for this particular cycle dq by t is more than 0, then what does this mean? This simply means q1 by t1 plus minus q2 by t2 will be more than 0. That means q1 by t1 will be more than q2 by t2, or T2 by T1 will be more than Q2 by Q1 multiplied by negative. This sign will get reverted. So minus T2 by T1 will be less than minus Q2 by Q1. Add 1 both sides. 1 minus T2 by T1 is less than 1 minus Q2 by Q1. What is this? This is the efficiency of Carnot cycle, and this is coming out to be less than efficiency of this general cycle. How can this be possible? This is violation of what? This is violation of second law of thermodynamics, or the violation of Carnot's theorem, where it says that if two engines are working between same temperature limit, then none will have efficiency more than that of reversible case. So Carnot cycle should always have a higher efficiency in comparison to a general or reversible cycle. So this is violation of second law, hence not possible. Hence, if in any process you are coming across a situation where dq by t is coming out to be more than 0, that simply means you have done something wrong somewhere, because for any possible process this dq by t has to be less than or equal to 0, less than for an irreversible case, and equality holds for a reversible case. So today's we will be stopping our discussion at this moment. Thank you so much for your patient hearing. If you liked my video, then please do subscribe.